Okay, here is exam 3, number 14. Now, since this is talking about numbers of things in a particular unit of time, probably I would go with, in A, I'd probably go with Poisson. I'll try to also look at this with binomial, which might be another option. But right now, for this video, we're just looking at the Poisson. Now, in part B, it says, let's get a maximum likelihood estimate of our parameter of the Poisson. Well, okay, so back up a minute, and our Poisson distribution, a probability of k for a given parameter lambda is equal to lambda to the k e to the minus lambda over k factorial, and that is for k equals 0, 1, and so on. Okay, so now we have these data where we have, well, a value. So if we think of this as k here, and number of times, some x or something like that, then 59 times there were 0 failures per hour, and 1, 2, 3 and bigger than 3, and 27, 9, 1 and 0, for a total of 96. Okay, now, so if we want to do a maximum likelihood estimate, what we have is actually there are 59, so if I start talking about like x1 to x 59, those were all zeros. They all had a k of 0, or k equals 0. And then x60 to x whatever, let's see, so that'd be 86. Those were all k equal 1. So we had, a whole lot of x's here, and with each x, we would use the particular k value up here to do that. And so similarly, we've got these others, and the 9 2 times, so k equals 2, k equals 1, and so 9 times, so that would be x87 to x95, and then x96 had a k equal 1. So there's our data, and so for our L of lambda, our parameter lambda, what we would have is we would have this lambda to the 0, e to the negative lambda over 0 factorial, and we would multiply those, so this joint distribution, 59 times, so we get that. And then lambda to the 1, e to the negative lambda over 1 factorial, we would have that, what was that, 27 times. We have lambda squared, e to the negative lambda over 2 factorial, and that was 9 times. And then just one time was lambda cubed e to the negative lambda over 3 factorial. Okay, so that's what we have for our data. So we could do this more generally, but that's our actual data. And so now I want to take L prime. Well, actually I want to do the natural log first. Don't want to take the derivative of that nasty thing. So I need the natural log of L of lambda. And when I take the natural log, you know, one of the first things I can do is break these up into pluses and then bring the 59 down. So I've got a 59 natural log. Now, lambda to the 0 is 1, so in this case I've just got e to the negative lambda. And then I'll have a plus 27 natural log of lambda e to the negative lambda. And then a plus 9 of natural log of lambda squared e to the negative lambda over 2. And then finally plus natural log of lambda cubed e to the negative lambda over 6. Now, so I can rewrite that. That's just minus 59 lambda for that first part. Then I have, I can break up the product under this one into a natural log of lambda plus lambda e to the negative lambda, but the natural log of e to the negative lambda is just negative lambda, so I'll end up with a plus 27 natural log of lambda and then minus 27 lambda. And similarly here with the 9, I'll get a plus 9 natural log of lambda squared, and then minus 9 lambda, and then also a minus 2 log 2 actually, so minus 9 log 2, and then finally plus my natural log of lambda cubed minus lambda, and then minus natural log of 6. Okay, now I can simplify this a bit, and this becomes minus 59 minus 27 minus 9 minus 1, all times lambda. And then we have these natural logs of lambda. Now this one I could bring the 2 down in front, make that 2 times 9. Here I can bring the 3 down in front, make it 3 times 1. And so I'll have plus 27 plus 2 times 9 plus 3 times 1, all times the natural log of lambda, and then minus 9 log 2 and minus log 6. Okay, now so this is minus 96 lambda and plus we get 18 and 3 is 21, so that's 48. 48 log lambda, and then minus 9 lambda of 9 log 2, sorry, minus log 6. Okay, so that's our natural log of L of lambda. And now if I take the derivative of that natural log L of lambda with respect to lambda, I get a minus 96 plus 48 over lambda, and 0 for these constants, and we get, we want to set that equal to 0, which says then that 48 over lambda is equal to 96, and so lambda is equal to 96, whoops, not 96, 48 over 96, which is 0.5. Okay, so that's what we get for lambda, if I did all my arithmetic right. And let's see, so yeah, so 48, okay. So 0.5, and so now, so I guess that's our maximum likelihood estimate. And so now C, if we wish to compute C, again, it requires 20 hours of computing time, Now, but any given hour, so what you have to remember here is that our probabilities with this lambda, what we've just fit is the probability of how many go down in a given hour, right? So our probability that, say, big K equals some little k is the probability that K fail in an hour, in a given hour. So let me say that as a given hour. Now, so if we view those as independent and so forth, then to stay up, in other words, don't have the whole thing fail, we would need 0 fail in 20 hours, or 1 fails, exactly 1 fails in 20 hours. But you see, this is actually a binomial distribution at this point, and so we do need our distribution that we just fit with a parameter of 0.5 to work this out. So we're going to need, where is it here? We need that to work this out, and so we've got k equals 0 and k equal 1. And so, you know, we have the probability that k equals 0 is lambda to the 0, so that's just 1. E to the minus lambda, but lambda is 1/2, so e to the minus 0.5. And then our probability that k equals 1 is equal to 0.5 e to the minus 0.5. Okay, so we get that for our two probabilities. And actually, I guess I misspoke. You know, I called it binomial, but not, it's not really binomial, I guess, now that, you know, now that I'm speaking to it here. Because you've got these two probabilities. But so what we need is the probability that k equals 0 to the 20th, because we need 20 straight hours where nothing went down, times the idea that 19 of these hours, and this is why I was sort of thinking binomial, is plus 20 choose 19. We need 19 of these hours, so probability of k equals 0 to the 19th to be 0, and one of those hours, k equals 1 to the 1, to be a down. And so we end up with this, which is k equals 0 to the 20th, that is e to the minus, what's 20 times 0.5? That's 10. And then plus 20 times e to the, I need 19 times that, so that'll be minus 9.5, and then times e to the k equal 1, so that's, oh, I lost my 0.5 there. So that's 0.5 e to the minus 0.5. And so that equals e to the minus 10 plus 10 e to the minus 10. Okay, let's pause it there. Okay, I had to go up and look at the probabilities. So notice this is not equal to, just to make sure I was doing it right, the probability that k equals 0 plus the probability that k equals 1. Because those, that would be, in this case, e to the negative 0.5, and then plus 0.5 e to the negative 0.5. So very different solutions. So you see, this is not the case. And on some of your papers, I realized, you know, I had mentioned binomial, but it's actually not binomial, in that these aren't successes and failures in here. But I was thinking of a binomial expansion, and that's why I had thought binomial. But this is what we want to do with those probabilities once we get them. And so our answer here for C under a Poisson distribution and maximum likelihood estimation would be e to the negative 10 plus 10 e to the negative 10, which, well, I don't have a calculator up on these. Whoops, I don't know what I just did. That was weird. I don't know if you saw that screen or not, but it came up and it asked me if I wanted to power off or restart. I did not want to do either one. So let me, I'm on my computer here, and I'll do a quick calculation. and see what that turns out to be. So e to the negative 10, and then plus 10. So that's really, what, 11 e to the negative 10. Silly me. Okay, so that's 11 e to the negative 10. And that is 0.000, essentially 5. It's 499, and then 399. So pretty much 3 zeros and a 5. Okay, so that is number 14.